Hey everybody, welcome back to another round of physics, and yeah, let's get going. Up to this point, we have seen circuits involving several different types of elements in combination, namely the idea that we can have, for example, batteries and capacitors, or we've looked at resistive circuits, say something with a resistor and batteries, or multiple resistors and a battery. What we have yet to do is actually look at what is called an RC circuit. That is a circuit that contains, for example, a battery and then a capacitor and resistor. And so I thought, well, first of all, we should do some basic analysis of this type of circuit, and then maybe in another video we'll do several example problems of increasing complexity just to kind of get an idea about what's going on. Now, as I've mentioned in lecture, when we're doing circuits like resistors, or if we did a capacitor, we have assumed that the circuit very quickly hits a steady state. Or another way to say it is we have completely ignored the transient behavior of the circuit as it reaches equilibrium. So you know that, for example, if we throw a switch into this circuit and we close the switch, there is a brief instant in time where at different parts of the circuit, the current is different. Now, for this transient nature of the circuit, we are assuming what happens is that a current, say, at one location is different than a current at a different location. Okay? When we're considering the RC circuit, what we will see is that the current does vary, but not spatially. In other words, at every point in the circuit, the current is the same. However, we will see that the current varies in time. Okay? In other words, that we will see the time-dependent nature of the current. So I want to just be clear that we're not dealing with the transient time that it takes the currents to reach equilibrium. We're dealing with something else. Now, how do we actually approach this? Well, let's say that we have a potential of the battery. We'll call that V. We have a capacitance and we have a resistance. And just like how we approach any other circuit analysis, if we want to know the full-blown story on the whole thing, how we'll approach this is using Kirchhoff's laws. And in fact, right now for this simplified circuit, we have only one loop. We need to choose a direction, so I'll arbitrarily choose that direction. Now we should label the highs and lows. So I'll go ahead and label the highs and lows. Now we say we have one unknown, the current. And so now we need to simply apply Kirchhoff's laws until we have all of the number of required equations. Here, because we only have one current, we only need one equation. And we see that KCl won't do us any good because we don't have any junctions. And so KVL is how we'll have to approach this problem. Well, let's go ahead. KVL tells us the sum of the jumps is equal to the sum of the drops. And therefore, as I walk around the circuit, we have the potential of the battery is equal to the potential drop across the capacitor plus the potential drop across the resistor. Now we'll go ahead and substitute in our expressions for the potential drop across each of these circuit elements. And we get that the potential drop across the battery is the charge on the capacitor divided by the capacitance plus the current flowing through the resistor times the resistance R. Excuse me, I'll use a lowercase q here. Now you might say, as a brief byline, why'd you use lowercase q and lowercase I? And the issue is that the textbook that we'll use next term uses that sort of notational convention. Capital I and capital Q refer to quantities that are time independent. And the book will use a lowercase I and a lowercase q for quantities that are time dependent. Okay. So I thought that although that distinction isn't made in this class, nor is it made in our textbook, it's always good to start getting used to some of that notation because we will see it in the future. Okay. Well, we now have completed our Kirchhoff's equation, right? We have V is equal to Q over C plus I times R. Okay. And now here we will notice that we actually have a differential equation. Namely, if I recall, the charge that goes onto the capacitor is equal to the current running through, well, excuse me, I shouldn't say equal to, I should say it's related to the current running through the resistor. And in other words, we could rewrite this as V equals Q over C plus R, I'll move that in front, and then we have a time derivative of the charge. Noticing that the Q that I've written for the capacitor, that is the same Q that's involved right here in the current. Mathematicians call this type of differential equation a first order because the highest derivative that we see in the equation is a first derivative. So first order. Okay. The second thing is that we notice that for each of these terms, we notice that the term out in front are constant. Constant. Okay. So we say that there's constant coefficients. Okay. You also notice that the unknown variable is raised to the first power, right? Q is raised to the first power, and so that makes this equation linear. And lastly, because the potential is time independent, we say that it is homogeneous. So altogether, how a mathematician would describe this equation is a first order homogeneous linear differential equation and I guess you could say with constant coefficients. Now, part of the reason that mathematicians are interested in this terminology or doing this procedure is that each of these ideas that are expressed here are fundamentally tied into how do we solve the equation. So, for example, there are certain techniques for solving first order equations. There are certain techniques for solving homogeneous differential equations. There are certain techniques of solving equations with coefficients that aren't constant. So these are the kind of the key properties of a differential equation that help lead to certain ways of solving the equation. Now, for example, I could say that a first order homogeneous differential equation with constant coefficients always has a solution. Okay? And so we should go through and show how to get that solution. Yeah. Mm-hmm. Now, this terminology, again, you'll see it in Phys 245. You don't need to let it keep you up at night, but as you start seeing it, you should, in the back of your head, kind of remember certain things about it. So, so we'll leave it there. But how do we go about solving this? Well, the first thing I'm going to do is I'm going to do something kind of wonky. I'm going to go ahead and take a derivative. Okay. This is not the only way to go at it. You could sub in for example, if you've had 245, you could sub in something called the characteristic equation and be perfectly fine. I am not going to do that. I think I'll just do it this way. I'm going to go ahead and take a time derivative of both sides of the equal sign. Now, you know that taking time derivatives, if I take a derivative of one side of the equation, I must do the same thing to the other side. Okay. Now over on the left-hand side, remember that this V does not vary in time. It is the potential of the battery. Yeah, very good. So the time derivative of that gives me a 0. Okay. Now on the right-hand side, I'm going to back sub. We used this idea that the current is equal to the change in the charge per unit time. And I'm going to just substitute that in because what we see, and this is for visual simplicity, okay, what we see is that this one is a derivative of the current plus the current divided by the capacitance. Okay. So sometimes it's hard to see that kind of relationship, so I just went ahead and put it back in. Okay. Well, it turns out that this equation that we have written here is always separable. I can always get the current on one side of the equation and all the rest of the GAC on the other side. So let's go ahead and do that. I notice that if I move one term over to the other side, I get negative R di dt. Okay. And now I'll move everything around to get the i's on one side and the t on the other. I'm going to go ahead and move that r while I'm thinking about it. Okay. And I've gone ahead and separated it. Now, all that's left to do is that we need to integrate. So I will go ahead and integrate both sides of this. Now, I don't have limits of integration right now, so what I'll end up having to do is tack on the integration constant. So as I integrate that, of course, the right-hand side of this equal sign, piece of cake, that's just a t over rc. And I'll go ahead and add in the integration constant. Now, so that I don't mix it up with the capacitance, I'm going to put an extra bar in there just to remind myself, like, yeah, that's an integration constant, not a capacitance. Now, on the left-hand side of this equation, yeah, good. That should ring a bell. The power rule doesn't work here, unfortunately. This is defined as the natural log function. So we'll go ahead and put that in there. Well, I want I by itself, so let's go ahead. How do I undo the natural log? Yeah, I raise everything to the power of, well, I take e and raise it to the natural log of the number. So these are inverse functions. So, and everything I do on the left-hand side, I got to do on the right-hand side. And because e and ln are inverse of one another, that just leaves me I, the current. And what I have on the right-hand side is e to the negative t over rc plus this integration constant. Well, now I'm going to take advantage of the rules for exponents. Usually what we end up having is two numbers of the same base being multiplied together and we add the exponents. I'm actually going to go the other way right now. I have exponents that are being added. I want to kind of undo that. And so how I can undo that is that's the same thing as e to the negative t over rc plus, times e to this integration constant c. Now here we'll just play a little, I don't want to say trick, but this is kind of how we'll do it. C is a constant, but e is also a constant. So taking a constant and raising it to a constant is just a constant, right? It's just, I'm just going to lump it all together. I don't really care what the value of the integration constant is. I care about the coefficient out in front. So let me relabel this. I'm going to just call this entire term, I'm just going to call it A. Okay. And so what we have here is that the current as a function of time is simply some amplitude, A, e to the negative t over rc. And there is our solution, well, almost. There's almost our solution for the circuit. Now you could say, wait a minute, Greg, I don't care about the current. I want the actual charge, Q. Okay. That's not a problem. Don't forget that this is dq over dt. And so what we could do is simply integrate that a second time. Notice that there's no charges on the left-hand side here. And so we could end up with something that says dq is equal to some constant e to the negative t over rc dt. And we can integrate a second time. So at the end of the day, we have q is equal to some constant. Now go ahead, take the integral of that. Yep. Right, you said, oh, okay, well, this is just some excuse me, this is just negative RC e to the negative t over RC. And we'll put in a second integration constant. I guess I'll call that b. And technically we're done. Now, of course, there is another thing. You could say, wait a minute, Greg, this isn't done yet. I don't know the value of these integration constants, what I've called a and b. And I completely agree with you. You don't know them because those depend on the initial conditions of the circuit, or maybe the final state of the circuit. So we have to go back and look. But these constants, these integration constants, we can't get those by some equation. What we have to do is we have to get those by looking at what is called the initial conditions for the circuit. Okay? And that is where we take the math result, what I have displayed on the page for you, and apply it to our actual circuit that we're dealing with. Okay? In some sense, this is true for any RC circuit that you can come up with, right? I mean, I should say battery, resistor, and capacitor in parallel. So that's the solution to every one of those circuits. The only difference between any of those circuits that I can build is what are the initial conditions. Maybe the capacitor is partially charged. Maybe it's the battery is a 10 volt instead of a 9 volt. Okay, so those little details are the thing that will dictate those integration constants. We should go back and look more carefully at our circuit. So if we remember, we had a capacitor and we had a resistor. Let me draw that resistor better so that it actually looks like a resistor, right? I get a little fast sometimes. Okay. And there's two things that we have to actually think about the physical response of our circuit. Okay. Number one, imagine rather than having just a circuit here, I'm going to throw in a switch. Okay. And it closes. Okay. Now, question, at time equals 0, so the instant that the switch is thrown, okay, how much charge is on the capacitor? Yeah, good. You say there is none, right? If I have an uncharged capacitor and I throw the switch, the instant that the switch is closed, the charge on the capacitor is 0. Okay? And hopefully you can see this gives me a way of figuring out one of those integration constants. In fact, if we were going back and doing the integrals, maybe we should say at time equals 0, the charge is equal to 0. Okay? That's where that comes in at. So another place that's always helpful to look at is as time goes to infinity. Now that one might not be as immediately apparent as what I should put in here. So let's go here. As time goes to infinity, what can you tell me about the amount of charge that's stored on the capacitor? Yeah, good. It shouldn't change anymore. The capacitor becomes fully charged. Now, if the capacitor is fully charged, what can you tell me about the current running through the circuit? Yeah, good. If the capacitor is fully charged, the current running through the circuit is equal to 0. Which means, what can you tell me about the potential drop across the resistor? Yeah, good. the potential drop across the resistor should be 0 because there's no current. Okay? So if the potential drop across the resistor is 0, what can you tell me about the potential drop across the capacitor? Yeah, good. Good. So if the potential drop across the resistor is 0, the potential drop across the capacitor must be that of the battery. Okay? And then we can say, hey, there's a relationship between the potential drop across a capacitor and the amount of charge on the capacitor. So at the end of the day, as Q goes to infinity, the total charge must be the capacitor value times V, the potential of the battery. And that these two conditions will allow us to take our general equations. These are perfectly general from math. And it will allow us to tailor those general equations to the specific situation that I'm handling, namely an uncharged capacitor that is being charged. Okay. And incidentally, I'll work this in terms of variables so that, it doesn't matter what the capacitor is, it doesn't matter the resistor value, the battery value, it'll all work out. Okay. We'll have a generalized solution for an uncharged capacitor. Well, let's go ahead. First thing is that we said, so let's go ahead and plug in our first initial condition, namely that at time equals 0, the charge is equal to 0. So I've written that out for you. And of course, the nice thing about this is e to the 0 ends up being 1. And we said that the uncharged capacitor has no charge to begin with. And this tells me that negative RCA plus that integration constant B. So I get that B is equal to the resistor capacitor times the value of A. Now we have to go to our second initial condition. Namely, our second initial condition said that the charge at time is equal to infinity. Well, here we have to be a little bit more careful. I'll put negative T over RC plus plus B. And here, okay, I've got to be a little bit more careful with my notation. Technically, we can never get to infinity, but I take the limit as T goes to infinity. Well, we already argued that in that limit, the potential drop across the capacitor must be equal to that across the battery. And so I must have a total charge of C times V stored on the capacitor. On the right-hand side, we notice that as T gets very large, e to the negative T gets very small. Good. Don't forget, you can write e to the negative T. That's equal to 1 over e to the t. So if t gets really large, e to the negative t gets very small, close to 0. Now I know you said, Greg, there's an RC in there. Of course, but some really large number divided by some small number is still a large number. So the reality is that this term, this first term in our expression becomes 0. And I get that my constant B is equal to the capacitance times the battery potential. But we still have to back substitute now. And if this is equal to B, that means that A is equal to CV over RC. And you say, oh, goody, goody. Right, we're taking this result and substituting it back into here. You say, oh, goody, goody. That means that our constant A is just equal to V divided by R. Well, let's go ahead and plug those in. So now we have that Q of T is equal to, we had V over R times the quantity negative RC e to the negative T over RC plus, now B we said must be CV. And we could go ahead and simplify. Notice I have the goody-goody moment. The R cancels the R. And I get something that says, now I have CV out front. So we have a common term of C times V. So I'm going to pull that out. I get 1 minus e to the negative t over RC. Oh, by the way, my current as a function of time, if you remember, it just had A out in front. And so my current as a function of time is simply the potential of the battery divided by the resistance, e to the negative t over RC. And there we go. Here are the two solutions. Well, it's a single solution, but it depends if you're interested in the current or if you're interested in the charge. There are the two solutions that are for a charging I'll call it de-energized capacitor. Pretty cool, huh? And yes, I'll go ahead, but of course we could plot these values, we could plot these functions, and we'll see that if I plot Q as a function of t, oh, excuse me, this is time. If I plot Q as a function of t, what we will see is that this will reach asymptotically some value of C times V. In other words, we'll get, and it'll level off asymptotically. Okay? Now you say, well, how fast it levels off, we can talk about that, but the general shape will be in this manner. Okay? Similarly, if I plot the charge as a function of time, the current as a function of time, what we'll see here is that it will start, we can plug it in, of course, it will start at t equals 0. It starts at a value of V over R, as if the capacitor weren't there at all, and it will exponentially decrease to 0. Pretty cool, huh? And yes, there's a couple of extra little notes that I need to put in here. Number one, notice that when you have a de-energized capacitor, for a brief moment at time equals 0, it's as if the capacitor weren't even in the circuit, right? The charge on the capacitor is 0, which means the potential drop across the capacitor is equal to 0. So for a brief instant in time, the capacitor acts like a perfect wire, just for that brief instant. Now, of course, at long times, when t goes to infinity, now the potential across the capacitor is equal to the potential across the battery, and current stops flowing. So at short times, right, at t close to 0, the capacitor is acting almost like a perfect wire. At long times, the capacitor is acting like a break in the circuit. It no longer allows current to flow through the circuit. And that is a behavior unique to capacitors. Now, sometimes, as we'll see in the future, I don't remember these equations. I don't like having to rederive them, but how I remember it is with that kind of idea right here. At short time intervals, capacitor acts like a wire. At long time intervals, it acts like a break. And that helps me remember which equation goes where. The other thing that I should talk about is the exponential. Now, all of the equations that you'll have dealing with RC circuits and actually some other circuit types, they tend to have a term like this exponential raised to the negative t over RC. And so we should take a little bit more time to talk about it. First of all, let's look at the this term. Of course, the negative sign simply means that E is getting progressively smaller as time progresses. Okay? And we should ask ourselves very quickly, what are the units of R times C? Or a different way to say it, what is a ohm times a farad equal to? Yeah, it's not easy, right? I mean, we could go through and do our dimensional analysis. We know, for example, from Ohm's law that V is equal to IR. And so an ohm must be a volt divided by an amp. Okay? And similarly, we could say, well, a farad must be a coulomb divided by a volt. All right, and that one comes from a capacitor is equal to, a capacitance is equal to a charge per volt. And now you say, oh, goody, goody. Maybe I should have done an equal sign. You say the volts cancel, and I have a coulomb divided by an amp. But then we remember that an amp is simply a coulomb per second. And you go, oh, goody, goody, the coulombs cancel. And it turns out that when I take a resistance times a capacitance, the end unit is actually in seconds. It's cool, right? It is for this reason that the value of RC, when you're dealing with these equations, it is sometimes redefined as, you'll see it as tau. Okay, so the lowercase tau Greek letter. Maybe I shouldn't use the Greek letter in actually spelling it. Okay. It's called tau, and it is also referred to as the time constant. So there might be books where rather than writing e to the negative t divided by RC, they might end up writing it as e to the negative t divided by tau. Now, the advantage for using that sort of notation is that when one time constant elapses, say when t is equal to 1 tau, you know immediately that you get something like 63%, something like that. Okay. Or for 2 tau, for 2 time constants, if 2 time constants elapse, if I recall correctly, you know what, I've got this backwards. That's not 63, this is like 33. 2 time constants is going to be something like 10%. And I think that at 3 time constants, it's something like 5% or 3%, something like that. So sometimes, rather than dealing with the resistor and the capacitor separately, you'll get a quote for a time constant. And that tells you, the time constant tells you how quickly the current decays, or it's indicative of how quickly the capacitor charges. Okay. And you can see that to a degree. If R is large, is really large, then the time constant, tau, ends up going up. It takes a longer time to charge up the capacitor. You could say, well, wait a minute, how would that work? Well, let's think. What's the purpose of a resistor in a circuit? It is to remove energy. Okay? So imagine for a second, a resistor's job in a circuit is to remove energy. What's the job of a capacitor? To store energy in the electric field. So imagine if you have a resistor whose purpose is to remove energy from the circuit. You have a capacitor whose job is to store energy in the circuit. What ends up happening is that it takes longer for the capacitor to charge up because some of the energy is being removed by the resistor. Okay. I should say the battery provides a constant energy. right? A constant change in electric potential. So we could think of that as being, for this given circuit, a constant energy. So some of the energy gets invested into the capacitor, the rest of it's getting removed by the resistor. And so therefore, it's going to take longer for the capacitor to fully charge. And you could say similarly, if the resistance is very low, not much energy is being removed from the circuit by the resistor. Therefore, there's more energy to put into the capacitor, or there's more energy for the capacitor to store, and therefore the capacitor should charge faster. Similarly, if the capacitor goes up, you could think of this as having a larger briefcase, a larger suitcase to store things in. Okay. So that would make some sense that if the capacitor goes up, I can store more energy in the electric field, and therefore it should take a longer time for me to actually get the capacitor filled. Okay. So tau still goes up. So that's why sometimes people like to think of the time constants rather than the individual components. Okay. So I think that's probably enough for this lecture. One of the things that you should probably go and do on your own is see if you can apply Kirchhoff's voltage laws for the discharging capacitor. I'll go ahead and have a brief video on that. It won't have any additional discussion. It'll just be, maybe a 5-minute, 10-minute video doing that, just so that you can see the derivation. But I encourage you to try it out first, just so that you have some sense of the approach. So that's it for all right now. Thanks for your attention. Keep up the good work. I'll see you next time.